叫什么？
韩面。
你是韩面生。
然后中文名叫什么？什么名？艺名。
你这是安排奖？
这是18年出的那个派的嘛？我没买 Pro， 因为太挺贵了。
对啊。
对啊，之前买这个，我发现它就是18年出的都很用那个pencil，所以我就干脆直接买了。然后我正常情况下说，我专辑一个9 Pro 的，然后一看说价格，我说价格好像是149，然后当时有discount的是599，有点计算的，还不是12.5寸的，太他妈贵了，我操！我他妈还要再他妈加点钱，我换一个小麦什么的。
对，我们学校买的那个苹果免税
是吧？我他妈从同学那儿能买个75折的，但不知道他苹果员工嘛，他们75折，我不知道他那有没有税什么乱七八糟，我就没托他买，他是挺神奇的，他就告诉我有名额限制的，你要是买早点到，要不75折就光了，就只剩9折了，我说好吧。
So just to continue the announcement, so this was the same as last time. So 4.0 I think is now unmuted, so you should be able to see your grades. How is that right?
Yes, that's great.
Yeah. So you should be able to see your grades. And homework 1 is posted, start early, and these are just the same stuff that I had last time. Okay, so whenever you write a solution, make sure you have all algorithm description, proof of correctness. I've had some questions over email about how detailed to write these things, and hopefully I've answered many of the questions. Okay, so alright, so last class we started looking at divide and conquer algorithms. We said that the basic idea here is you break a problem instance into multiple sub-instances, okay, and then you solve them separately and then you combine these solutions. Right, and the art is often in how you break it into smaller pieces and how you combine solutions. So, and the middle part is just done recursively. And in all the examples we've seen, the instances that we create are actually disjoint. Okay, so like you break up the problem into like disjoint pieces. Although in the multiplication example, it's not quite disjoint, as we will see. Okay, so, but as I said last time, it's not really necessary, and we'll touch upon that today. Okay, so, and we also saw this merge sort algorithm. We saw very detailed analysis of this. And I also spoke a little bit about how you solve recurrences. Okay, and recurrences show up when you try to analyze divide and conquer algorithms because there is the recursive step which you've got to analyze. And this is where recurrences show up. And I said that there's 3 kind of broad ways of solving recurrences. One is just guess the answer, prove by induction. The other is you try to like manipulate the recurrence equation until you actually get to the solution. And sometimes you may not do the whole thing. You may stop midway, guess the answer, and then go to the first one. Yeah.
So the master theorem is kind of a way of solving this theorem, right?
Yeah, so right, I should actually mention that there is another thing people often use, which is called the master theorem. So it is, so it's a theorem that applies to a specific class of recurrences, and which commonly show up. Okay? But so the reason I don't do this explicitly is because I think the name promises more than it is. Okay, so it's a very special, it is for a very special class of recurrences, and for these things it gives a closed form solution. Okay, and you can pretty easily derive the master theorem. Okay, so it's not, so if you want, you should look up any of the standard. I can give a link on the home page. So there is nothing really masterful about this. So it's for a very specific class of recurrences. And so this recurrence tree is another way of essentially having a visual representation of this like plug-in chug type. Yeah.
So, I mean, if we're asked on a homework to prove the complexity of something, would it be sufficient, like acceptable to say, yeah, the Master's theorem applies here because X, and then show the working conditions?
So you can use master theorem. There's also this a little bit more. This also some of you might know. There is this thing called the Akra-Bazi theorem. How many of you heard about this? Oh, surprise. Okay, so this is a slightly more general form of master theorem, and it subsumes it and it also extends to other cases. Okay, so this is another thing you can use, and in general in these like initial homeworks, feel free to use anything. Just state what you are using. Like you don't have to prove it, but if you are using the master theorem, just state which version of it you are using. So that's it. Then same goes for this Akra-Bazi. Alright, so again, so this is a picture of divide and conquer that we saw last time, and these parts don't have to be destroyed. Alright, so what is today's plan? So I'll continue the examples where we left off last time. So we left off with integer multiplication. Okay, so we'll continue that. And I'll also talk a little bit about a slightly non-trivial example of divide and conquer, which is what's called median finding. Maybe some of you have seen both of these before. And we'll also start with a quick introduction to dynamic programming. Okay, so that's the plan for the day. Right? So let's go back to this example we started looking at last time. Okay, so you've got two n-digit numbers. Okay, we call them A and B. Each one has n digits, so they are like pretty long numbers, and you should think of n as being really large. You think of n as being a million. And you might wonder why you multiply million-digit numbers, and some of you may know there are a lot of applications for this. Okay, like a lot of cryptography rests on these kind of things. Okay, so you really want to multiply big numbers in some application. Okay, so that's so that's why this is a basic. And we said that the elementary school algorithm, where you basically write down the number, multiply digit by digit, and add all these results up. So we said that this takes time n squared. Okay, so I had an example last time, and we saw it takes time n squared. Okay, and right, and then we started looking at divide and conquer algorithms, right? Because we'd like to see if you can do better than n squared. And what we started with last time was the following. Okay, so this is all stuff we did last time. So you had A and B, which were your n-digit numbers. So these guys were n-digit. Okay, we broke them up into two pieces, each n by 2, n by 2. And then we asked ourselves, okay, so what does it mean to break up an integer A as two pieces x and y? Said that you can write A as 10 to the power of n by 2 times x plus 1. Okay, because 10 to the power of n by 2 times x, so this is basically a number that is x followed by n by 2 zeros. To this, if you add 1, the zeros get replaced by 1. Because there's no carry anywhere. Just what. Okay, and the same with b. Okay, so you can write b as 10 to the n by 2 times z plus 7. Okay. And now a times b is very easy to compute. Right? So a times b is just the product of those terms. So you expand it out and you get this. Okay. And why did we do this? Because now these terms are products of n by 2 digit numbers. Okay. And now you can try to use divide and conquer. You can say that suppose you recursively compute these products. Okay. which you can do because now these are like n by 2 digit numbers. And then you add these up according to this equation. Okay? And we said that adding is just a linear time operation because once you have xz, 10 to the n times xz is just xz followed by n zeros. And now you're adding numbers that are all roughly 2n digits long. Okay, so this is adding 4 numbers. Each roughly 2n. So the last one is actually only n digits and these have like 3n by 2. But let's just be generous and say that everything has at most 2n digits. Okay, so this addition takes O of n. Okay, so this gave us this basic recurrence for this problem, which is T of n is 4 times T of n by 2 plus O of n. And this we somewhat hurriedly solved last time. Right, so we basically said that you have T of n equals 4T of n by 2 plus O of n. Okay, and this, I'm not going to do this again, but hopefully you guys have had a chance to revisit this and figure out what this is. And for those of you who know, this is actually a pretty simple thing to solve. So you end up with T of n equals something like n squared. So O of n squared. Okay, that's the solution to this recurrence. So there are many ways of seeing it, one of which is the master theorem. Okay, or you just do calculation. Okay, so a little bit of calculation and you'll see that this n squared. Okay. So what I was saying was, we put in a lot of effort, we came up with a divide and conquer solution, but this is not really improving over the elementary school algorithm. The elementary school algorithm was also n squared. Okay. So the question is if you can do better than this. Okay. So the main question we're going to ask is, can we do better than elementary school? Okay, so all right. So the key to this is this observation, right? So one reason to have hope is that, remember, if you look at this formula, okay, so A times B, we are writing it as something times xz plus something else times yz plus zw plus this yw, right? So you really only need these 3 quantities, right? So you need this guy, you need this, plus this, and these 3. Right? So one could hope, okay, if I want these 3 quantities, maybe I can just do with like 3 recursive calls. Okay, and those of you who've done homework 0, you've seen some mild examples of this. Okay, so where you had to come up with like a product using just a squaring operation. Okay, so this is something, turns out it's kind of along those lines. So the main observation of Karan Supa, so I think he's the one who first came up with it, is that this second term, okay, can actually be written as a product of 2 things minus the first term minus the third term. Okay, so you can write this as this term minus the first one that you've already computed, let's say, and the third term that you've already computed. So what this is saying is that if I want to find this middle term, and suppose I've already found the first and the third, then all you need to do is find this one product and then subtract these 2. And this is a very basic algebraic manipulation, right? And so this was his observation, that we need only 3 multiplications. So this is 3. So note that x plus y and w plus c are not quite n by 2 digit numbers, but they are almost so, right? I mean, they'll have maybe one more digit. Okay, so these are almost n by 2 digit numbers. Okay, so now you get a much better recurrence than before, which is that t of n is 3 times t of n by 2 plus 4. Okay, because you are calling, so you are only doing 3 multiplications. One is this guy, and others are those 2. Okay, so this is like a key trick that Karan, you have misspelled it. Karan Suba's observation. Okay. Yeah, and this is it, right? So now you have a different recurrence. The only difference, note, is that it's a 3 instead of a 4. Okay. Now you can ask what difference does that make, and now you can try to use this kind of plug and chug method, right? So you get t of n equals 3t of n by 2 plus some constant times n, which I'll write as c times n. And now you can try expanding this. So you can say that this is c times n plus 3 times c n by 2 plus 3t n by 4. So this is c times n plus, I'm just going to write it as 3 by 2 times c n plus 3 squared times t of n by 4. Okay. Okay, and now you can try to expand this the same way, t of n by 4 and t of n by 8. And so you will again observe a pattern that you get c times n plus, get this 1 plus 3 by 2 plus 3 by 2 whole squared, so on. So these will be like the first terms. Okay. And the second term will essentially be a 3 to the r times t of n by 2. Okay. So this is what the second term, this is what is going on in the recurrence. And you can evaluate both of these. So the first one will be something like essentially 3 by 2 to the r. So this is again. So what should r be now before you hit to the base case? Okay, log n to what base? Yeah, so, well, I mean, you were right, but you should justify that. Okay, so the base case always, some place where the answer is trivial to read off, right? And we know the t value only for t of 1, for n being 1. Right? So we know that t of 1 is 1. Okay, that's your base case. So you've got to go all the way until n by 2 to the r becomes 1. So when is so the base case is n by 2 to the r equals 1, which is like saying r equals log n to the base. And if you plug that in, so what will you get? So in this case, you will get so you'll get Cn times, so 3 by 2 to the r roughly speaking, because these terms will add up to something roughly like this. By roughly, I mean up to some constant. Maybe there is a small constant here. Okay, plus 3 to the r. And now you should ask 3 to the log n of the base. So what is 3 to the log n to the base 2? Okay, so this is some arithmetic which you're going on.
Don't you do the change in base theorem to get log into log 3 over log 2 to the 3, so it's 1 over
Just to change n.
Okay.
something like that anyway?
Yeah, so what you've got to do is, this is just basic, this is again high school math. Basically what you'll do is you observe that 3 to the log n to the base 2 is 2 to the power, okay, I have no space here. So it's 2 to the log 3 base 2 times log n base 2. Okay, so trust me when I write that this is basically n to the power of log 3 base 2. Okay, so this is, again, just recap your high school math in this word. Okay, so this is what this is. So this turns out to be smaller than this. Right? So what did we achieve here? Right? So we basically said that by replacing that 4 with 3, okay, you could move from a runtime of n squared to a runtime of something like n to the 1.5, okay, or n to 1.6, something. Okay, so this is the speed up that we gained by being a little bit more clever in how we did the combine step. Okay, and this is what is key usually to divide and conquer algorithms. When you're doing this conquer step and you're doing the combination, sometimes being clever can actually help you reduce the runtime. Okay, so that's yeah. So there is some homework problem also on something related. So when you're doing combine, sometimes being clever will do. Okay, so you could reduce from n squared to n to the 1.58, right? So now you can ask, can we do even better? Right? Like 1.58 seems like an odd thing to have to be like the right answer for this problem. Yeah, so it turns out that you can keep improving this by using roughly this idea. Okay, like you can divide into more pieces and combine them in more and more clever ways using some algebraic tricks like this. Okay, and in your homework you will see something that gets, I think, into the 1.35 or something like this. And it turns out you can keep doing something like this to get something like n to the 1 plus epsilon. So the kind of method I wrote, we have in the homework can get you n to the 1 plus epsilon for any epsilon. Now you could ask, okay, why can't I set epsilon to 0? Well, the constants end up blowing up. So there will be some constant term here which will be like 2 to the 1 by epsilon. So you can't really set epsilon to be too tiny. Okay, so, but for any constant epsilon, this is just a constant upfront. Okay, so this is a fast value. Yeah.
So was that like I guess is it known with multiplication if it's impossible to have a linear time algorithm for it? Do they have
Yeah, so that's what I was coming to. So this is one class of algorithms. There is another algorithm which hopefully some of you have seen, which is, yeah, have you guys seen any other algorithms, faster algorithms for multiplication? Yeah.
Isn't there so many things like an FFT?
Yeah, so there is an algorithm based on what is called fast Fourier transform. Okay, so this is, one can think of it as generalization of what I mentioned in the homework, and this ends up giving something like an n log n time algorithm. Okay, but the question that he just asked, can you get rid of this log n, is one of the big open questions. Nobody knows if you can do multiplication as fast as addition. Okay, like you can trivially do addition in O of n time. but we don't know if we can do multiplication roughly the same time. Okay, so the best we know is something like n log n. Okay, people have tried hard and gotten like n log n divided by some log, something like this, but we don't really know of, just an O of n time. So yeah, there's no problem. Okay, so as you can see, right, so I mean, even very simple things like this, sometimes we don't know the right answer. Alright, so this is something about multiplication. So let me give one other example of divide and conquer, okay, where it's not clear that divide and conquer can happen. Okay, so, and that is this problem that I'm going to. So this is called, so this is the problem of computing the median. So again, one thing about this course is that I'm going to keep throwing new problems at you, so you have to keep context switching between things. So this is, but most of the problems we will see are very standard ones. Okay, so these are ones that you should kind of know about, and they are kind of the representative examples of the techniques we will see. Okay, so let's look at this problem. Okay, so you have an unsorted list, which I'll denote by a0 through an minus 1. And your goal is to find the n by 2th smallest element. Okay, so this is a list of size n, and it's unsorted. Because I mean, if it were sorted, you can just read off the element. Okay, so your goal is to find the n by 2th smallest element. Okay, so firstly, how would you do this problem regularly? I mean, if you know the answer, then it's difficult. Yeah. Alright.
We could just sort the array and then.
Okay, so the most reasonable answer is sort the array and output n by 2 small. Okay, so this is the most natural approach, is what anyone would first think of. And one can ask, okay, can you avoid the sorting step? Because sorting takes time n log n. Right? And the question is, can you do this in just linear time? Okay, in just time O of n. Okay, so that's kind of the question we want to get at. Okay, so can you avoid this log n? And yeah, so it turns out this is actually somewhat tricky. Okay, and for a while people thought maybe you can't avoid sorting, and then there's a very clever algorithm that somebody could come up with, and that turns out to be based on divide and conquer. Okay. And it's one of the non-trivial applications of divide and conquer, right? Because firstly, suppose I told you try divide and conquer on this problem, right? So how would you proceed?
Could you like try some sort of sorting type approach, but don't sort the full thing?
Okay.
Some
And
sort of
how
like
would-
accelerate it a bit, like because maybe you don't need to sort the whole thing, you only need to sort portions of it before you can prove that this is the median.
Okay, so actually, I'm sorry, I think I'm messing up the page layout here, but let's see. Give me a second. Okay, so I may mess up the page layout, but yeah, so let's go back to what you're saying. So you're saying, yeah, let's try some sorting style approach, but without quite sorting, right? Which is break up the array into two pieces. So attempt would be to say, do what you would do for merge sort, right? So you have this array, which which is of length n, and now you try breaking this up into two pieces. Okay, it's of size n by 2. Remember, you want to do divide and conquer. And you want to find the n by 2th smallest number in the entire array. Right, so presumably you say, okay, maybe I find the median of these guys, maybe I find the median of these, and try to do something. Right? But does it, what do you guys think? Does it have any hope of working? Okay, so maybe it's not immediate to see, but you'll realize that there's no real connection between the elements here and the elements here, right? Without really looking further into these arrays, you can't quite tell if, you don't even know, for instance, which side the n by 2th smallest element is. And so it's a little weird, okay? So it's not clear how to do divide and conquer. Okay, so medians of the pieces don't give much meaning to it. Okay, so this is kind of sad. Okay, so we don't know how to use this, in a clean way. Okay, but so one of the key insights towards solving this problem turns out to be the following. Okay, so one of the key insights is that if you had what I will call an approximate median, then you can actually use divide and conquer in a clean way. What do I mean by this? Okay, so let's write down these numbers, a of 0. So you have the array, right? So a of 0, a of 1, on to a of n. So let's write it down on the line. So this is the real line. Okay. And a of 0 is somewhere. A of 1 may be here, a of 2 may be here, and so on. Okay. So suppose you write them down. Okay, and what you want is some number which is out here, which is kind of the middle number. So this is these are the numbers. They are in some order. They are unsorted. So now, suppose I told you some number in this range, where these are like the middle n by 2 elements. Okay, so after I lay them out on the line, okay, so now this is like sorting them, right? So A1 is the smallest, A2 is the next smallest. So suppose I imagine sorting them, and I told you I just give you one of these guys. Okay, so let's say some element. Okay, which I guarantee that it's going to be one of these middle n by 2. Now, can you use this information in a clever way? Yeah.
So now at minimum, we only have to look at these and find the middle one of those.
What do you mean?
So this is, you give me some number in the middle range, or you gave me the middle range?
No, I gave you just some number in the middle range.
Oh, so then if you put everything smaller than that to one side and everything bigger to the other side, would at least be somewhere along our middle.
Okay. Yeah. So what he's saying is, suppose I know this element. Let's call this x. Okay. And instead of sorting the array, all I do is just break up the array into two pieces. I put everybody on the left of X into one subarray. So I'll create two new arrays. One I will call them B and C. So one consists of all the A's that are to the left of X. So these are like A1, A2, A0, so on. Another consists of everybody to the right of X. Okay. So this I can do in just linear time, right? Because I go through the whole array and I just I just identify who's on the left and who's on the right. Okay, and I put them into new subarray. Now suppose I am very fortunate and I found n by 2 things on the left and n by 2 things on the right. Then what happens? Yeah, then X is the median. Okay, so then you are in great shape. You've solved the problem. But but this is clearly off chance, right? So you could say, okay, maybe I have, let's say 2n by 3 on the left, and I've got n by 3 on the right. Then, can you do something better? Yeah.
Yeah, because you know that the median is on, because the left side is larger.
Yeah.
So you know that the median must be on the left side, and you also know that it won't be, it changes the problem slightly in the recursive case, because you're now not trying to find the exact median of that subportion, but you're trying to find, what is it, like something smaller, I don't know the exact term, but it changes which position you're trying to find slightly.
Okay, so so what his intuition is, okay, so you can now restrict yourself to an array that is only of size 2n by 3. Okay, that's the first observation. And 2n by 3 is a significantly smaller number than n. Okay, so in that sense you've made some progress. And the other thing is that you're not trying to find the median of this 2n by 3 thing. You're actually trying to find the n by 2 smallest element in this 2n by 3 sized array. Because the n by 2th smallest element of the whole thing is also the n by 2th smallest element of this. Because these were just numbers less than a certain point. Okay, so let me let this down. Alright, so the observation one, the first one is that we can now restrict search to a 2n by 3 sized array. Okay, and this is much smaller than n in our sense. So you've kind of significantly reduced the problem. Okay. And now the other observation is need to be careful because answer is not the median of this subarray. But the n by 2 smallest element. Okay. But this is, I claim this is fine. Okay, so what I'm going to do is, I'm going to treat the original problem as just one of finding the n by 2 smallest element. Okay, so our goal will be to find, to solve a more general problem, okay, which is, we change our goal solving a more general problem. which is not just finding the median, but given an array and some k, you find the kth smallest element. Okay, so this is totally doable, right? Like, I mean, in some sense, we will solve the more general problem, and you plug in k equals n by 2 in the end, and you will get the median. Okay, so we'll change our goal, and this is something that we sometimes do when you're trying to solve a problem. Okay, so you might be trying to solve a problem, but you realize that this more general problem is probably the more, is the right way to go about solving this special case. Okay, and this often happens when you're trying to design algorithm. So alright, so this is the one that we will solve. And okay, so now you can now write like a subroutine for this problem. Right? Now you can recurse onto this 2n by 3 sized set, and then you basically call it with k equals n by 2. So now the observation. Now 1 and 2 basically mean that so let's call this procedure select of an array and some k. Okay, so this is called the procedure. This is the procedure. I will call it selecting the kth smallest from an array. So then what we have observed from 1 and 2 is that select of A with n by 2 equals select of this B, which is all elements less than or equal to x with n by 2. Okay, because I know that there were 2n by 3 elements less than or equal to x. So I can work on this subarray, and I just call it with n by 2. And alright, so this is great, right? So now you have a procedure for finding, so if somebody told you an approximate median, now you can write down this kind of a recurrence, so this sort of a recurrence relationship. And now I claim that this lets you solve the problem very fast. Do you guys see why? Yeah.
Since you're O of n at every step, you're just adding lots of O of n's together so you stay O of n.
Yeah, so what you're doing is, if you try to write down the recurrence for this, the size of the set that you're working with keeps reducing by a factor of 2/3 in every step. Right? You've gone from A to B, B was just 2n by 3. And the amount of work you've done in this iteration is only O of n, because the only work you've done so far is in creating the subarray P. Okay. Let me write the recurrence and then I will wait so that you guys get this. So I claim that T of n now is T of 2n by 3 plus O of n. This O of n is time taken to create P. Time taken to subarray P. You know that to find B, you had to scan all of A, put everything that was less than x into B. Right? So that was what we were doing to find B. And so the time taken for n is this. Okay, so I will pause here and see why. Yeah. How do you find what? Right, so that I haven't told you yet. Okay, so I'm just saying, suppose there is some helpful oracle who can give you x. Okay, then this is the recurrence you would write. Okay. Yeah.
Is this
somewhat like similar to Quicksort, that is what we find, and then you get by with.
Yeah, so it is. So his question was, is this similar to quicksort? It's something we've not seen, but yes, this is very similar to quicksort, and we will come to this when we do randomized algorithm. Okay. So, but yes, so but for now, I'm telling you that there is some helpful oracle who is giving you an X, which has the guaranteed property that there's like 2n by 3 elements in the line. Yeah.
So why is it called approximate? And can we find the exact median?
And then you would solve the original problem, right? So if you can find if you can find the exact median, then you can solve the original problem, right? So the hope is that finding an approximate median is easier than finding the exact median. And then you can solve, and then you can try to write down a recurrence like this. And if I allow you some randomized guesses, how would you just find an approximate median? Yeah?
Grab a few elements and see which one is the median of those.
Yeah, so you could do many things, right? Like suppose I just, I know that the numbers are like this. If I picked a random one, okay, with probability half, I am in the middle half, right? Because it's uniformly random, right? So I have a equal probability of picking any of these guys, okay? And it's kind of unlikely that I'll pick things towards the corner, right? So intuitively, finding an approximate median is an easier problem, okay? Because just a random one will, with some reasonable probability, be an approximate median. And we can also do something a bit more sophisticated, like what he said. You could probably sample 10 things at random and pick the median of those guys. So that was, yeah. So that's, you will see in one of the homework problems that is actually a provably better way of doing it. Okay. So, alright. So, but anyway, so if you had an approximate median, then you end up with an equation like this, okay, for your running time. And this has a very easy solution, because now if you just do this, you write this as again c times n, like we always do. And then you get c times n plus c times 2n by 3 plus c times 2 by 3 squared n plus so on. And this is a geometrically decreasing sequence with where this ratio is less than 1. And this adds up to a constant. Okay, so this is c times n and 1 plus 2/3 plus 2/3 squared 2/3 cubed plus so on. Okay. So, and this is some constant times some c prime times n. I think the constant is 3. Okay, so it's 3cn, which is some c prime. Okay, so this, this is just a geometric sequence, and this adds up. Okay, and so this says that if you are able to find an approximate median, then you are in great shape. Okay, then you reduce the problem size all the time. Okay. Yeah.
So for it to add up to less than or approximately 1 or some constant times that, then it's added up r minus 1 terms, right? Not r terms. And
yeah.
And you're picking 2/3 here, but if it's like approximate, and your median, shouldn't it be 1/2 of that, not 2/3?
Yeah. So this is a good point. So what he's saying is one has to be a little bit more careful. This is not always 2/3, right? Because so this gets me to the actual algorithm. Okay, so I've hand-waved a little bit here. So I've assumed that each time the array size reduced by exactly 2/3. Okay, and this can't always happen because maybe So let's just see. Right. So let's say the first time I found an x which had 2n by 3 things to the left. Okay. And this array I'm calling B. And I'm trying to find select of to n by 3, and I'm trying to find n by 2 at the smallest element. So this is what I just wrote. And how does this recursive procedure work? Okay, so this will now work with the array B, and it will find some element which is somewhere over here. Let's see. Okay, so this is in the middle portion of B. Okay. All I know is that it's not in the corners of this array B. Okay, so it's in the middle, n by 3 in this case. Okay, so it's in the. So what I'm asking is, how does call work? Okay, so firstly, it works on B, which is of size given by 3. And now, this approximate median finding algorithm would return me something which is in the middle half of B. Okay? So B had size 2n by 3. So the middle half basically means this is a range of size n by 3. Right? So it's somewhere in the middle of this. So maybe I found somebody out here. So I found an x prime which is out here. And remember that I'm actually trying to find the n by 2th smallest element of B. And yeah, so let x prime, and just for example, be the n by 3rd smallest element of B. So now your now where is your n by 2th smallest element of B going to be?
To the right.
It's going to be to the right of this guy, right? So you have to be a bit more careful. So the next time you recurse, you will actually recurse on this. So on this side, and now you will not try to find the n by 2th smallest element over there. You will try to do n by 2 minus n by 3. Right? Because you've got to subtract off how many of these guys were before. Okay? So your observation is now that n by 2th smallest element of B is the n by 2 minus n by 3th smallest element of this array on the right, which I will call B prime. Okay? Because I told you that x prime was the n by 3rd smallest element of B. And if I want to find the n by 2th smallest element of B, then I've got to look on the right, and I've got to find this. But this is still a select procedure. Right, so this is basically select on B prime this n by 2 minus, and that's the whole point. Okay, that you always can write it as a select operation. So I'm not going to go into the formal algorithm, but this is the way this algorithm works. Okay. So I'll have a link to some notes which will have the exact procedure for those of you who want. But this is the idea. Okay. So every time a select procedure will first find the approximate median. I haven't told you how that is done yet. Okay. And then it will call a recursive select procedure on an array which is guaranteed to be small. Okay, like a constant factor smaller than the original array. Okay. So the overall idea is select on A some k will first find approximate median B will make recursive call on a new array B, okay, such that So let's call this select of B with some k prime. So k prime will be different, like we saw in this example. Right? So you wanted to find the n by 2 smallest element of B, but you call n by 2 minus n by 3. So this will be k prime. Select B prime, new array of B such that size of B is less than some constant. Okay, so in our example we saw 2/3. It doesn't have to be 2/3, right? Anything less than 1 works. Okay, so for example, you could have like 3/4 size of B. So it could be 2/3, could be 3/4. Any constant less than 1 would work for that array. Yeah.
So do you always want to find the approximate median, or do you sometimes want to, I guess regardless of k, do you always want to look for the median?
Well, your ultimate goal is to find, is to, let's say, find the median, right? So, is your question that regardless of k, you will always find the median?
Yeah, is that what you
Yes.
always want to find, is an approximate median or an approximate, I don't know,
K thing.
second smallest element or something if k was equal to 2?
Right, so the way I'm describing it, so his question is, suppose k was a pretty small number. Okay, suppose k was n over 100. Okay. Will I still want to find the median, or will I want to find something between 0 and n by 50? Right, so that could be one goal. But the way I'm describing it, I'll always try to find the median. Okay. And up to constants, this is fine. So, but that's a good question. Like sometimes, if what you want to find is pretty small, maybe you don't want to find the median, maybe there's other ways of doing it. So, but it turns out this is almost as good.
Like so it won't like break down or anything if k is very small.
Yeah, so that's what, you can go convince yourself, right?
Okay.
Because because this algorithm is very simple. All it's the only thing I'm using here is that if approximate median is fast, then I'll always reduce the array size by a constant. Okay. So if I wrote down a relation like this, a recurrence relation like this, I will always get some c times n plus c times some constant less than some constant less than 1 times n, then I'll have this constant squared and so on. All I need for this summation to converge to to O of n is this constant being strictly less than 1. I could have had 99 by 100 for all you know. Okay, and it would still converge to a number that's just that's independent of n. So, alright, so that's the idea. Okay, that you first find the approximate median, and then you make a recursive call on a new array B which is strictly less than cycle. Okay, and so the exact details are not very important, and so I will link to some lecture notes from elsewhere, into notes that actually give details. All the textbooks that I've listed on the course page will have the details of this for those. Okay, but the idea is just this. Okay, that you find the approximate median, then you reduce the size of the array by some constant, and just converges to linear time. Okay, so that's what we will do. And now you should ask yourself, okay, so this relied on this crucial first step of finding the approximate median. How are you going to do this? Okay, so here again I'm going to do a little bit of hand waving, and actually there's a very simple picture that at least to me the first time I saw it, I thought this is, I just got it, right? So let me just draw that picture. Okay, so the idea is you have this array A0, A1 up to AN. So now the trick, so this is, I must tell you, this is a trick. Okay, so this is, I could not have come up with this. Okay, so the trick is you first group these into some constantly many buckets. Okay, so I write up to A, let's say 9. Okay, so these are like 10 things here. Then I do A10, A11, so on. So there are n by 10 groups of size 10 each that I've grouped these guys into. Now what I do is I will sort each of these guys, each of these small arrays. Okay, these are only of size 10, so I can sort in constant time. Right? I mean, I can literally sort them. Okay. And so imagine that I have sorted them and these were the sorted values. So let's just pretend that you've locally sorted them. Okay. And now I look at the median of these guys, which is like A of 5, let's say. And I have these numbers. Okay. And suppose I inductively find the median of these numbers. And this is going to take time, that is t of n by 10. Right? Because this is an n by 10 sized array. Okay? And this is going to take time t of n by 10. And so I found this guy, let's say, which is in the middle of these things. And now, can you guarantee that this is an approximate median? So note that, so in this picture I'm pretending that these guys are all sorted. And I'm also pretending that I've put this in the middle, so in some sense these were sorted, right? So can you give me a whole bunch of, like suppose I looked at this as the x. What can you say about x? Is this an approximate median of the whole thing? And why is this?
There are something on the left and something on top that's smaller than this one.
Yeah, so the idea is that everything in this quadrant is smaller than x. Okay? And everything in this quadrant is larger than x. Okay? And it'll take a little bit of effort for you to see this, but roughly n by 4 elements are less than x. Roughly n by 4 elements are bigger than x. Okay? And that's the magic of it. Okay, so now you found an approximate median, and so in some sense you're done. Okay, so this is how you find the approximate median. So again, I'm not going into the details because I want to give you like a pictorial proof of why. How you can find an approximate median in time that's not too large. Okay, so it will still take time t of n by 10 plus some O of n. Because I have to do this local sorting and I have to make that recursive call. So you will end up with a recurrence that's a little bit more harder than this. Okay, but it won't be too hard. You will end up with a recurrence that looks like t of n equals t of n by 10, which comes from here, plus O of n plus t of 2n by 3. Something like that. Okay. And the cool thing is that this also solves to just linear time. Okay, so you can prove this again by induction if you want. Yeah.
So I guess why not in this case too? It seems like if you find the medians this way, couldn't you already have the recursive steps since you know that the median, I guess if this is true, if n by 4 are larger than n by 4 are smaller, that you know it's either going to be x or those two that we don't know about, and that will be where the median is?
Right, but you don't know exactly how many are less, right? And you are guaranteed that there were so many, and then there's things on top, and so remember, only these local things were sorted.
All right. Yeah.
Yeah. So this picture is a little bit deceiving because it's assuming that these guys were sorted. You're not actually sorting these things, right? So this is just for our thinking. It's like hypothetically we are sorting these things because all we want to do is argue that less than x there are n by 4 elements. So we could imagine sorting them without actually sorting them. Okay, and that's what this picture shows. Okay. So yeah, so that's what's going on. So this is a very cool algorithm. Actually, I forget the names of I forget who came up with this, but this is actually, if you look at the names, it's like the list of who is who in theory. So it took a while and a lot of smart people to come up with this one. Yeah.
What about the worst case?
It is. This is a worst case bound because there is no probability involved, right? So this is just T of n is T of n by 10 plus. All right. So this is the median algorithm, and this is one of the classic examples of things where you may think that finding the median or finding the kth smallest element requires you to sort, but it doesn't. Okay, so you can actually do this without sorting the whole array. And yeah, I guess it's also one of the standard interview questions because you don't expect this to be possible. All right, so this is the approximate sorting, approximate median algorithm. All right, so let's do a brief overview of what we've done. Okay, so I gave you a bunch of examples. Yeah.
Sir, in the previous algorithm, there was no conquest here, like the median one.
So you can think of the. Yeah, you're right. I mean, there's no explicit conquer step because I mean the conquering is happening implicitly when you're trying to find this n by 2 minus n by 3 smallest element, right? Because yeah, so here you're not really solving both the subproblems, right? So yeah, so this goes back to what exactly is divide and conquer. Do you actually have to solve each piece, right? So here you're not solving both the pieces. In fact, you're taking care to avoid solving both the pieces, right? You're trying to solve only one of them. Okay. So in this sense, you're right. So what he's pointing out is that this is not technically in this picture that we've drawn of divide and conquer, right? So it's not like breaking up into pieces, solving these pieces separately. Okay, so this is just a clean way of reducing the problem size. Okay, so yeah, so in many of these cases, it's I mean it's a subjective thing. I mean it's a name, right? You can either yeah. So I don't want to explicitly list out what is a divide and conquer algorithm. But, yeah, but this is a good point. There is no explicit divide and conquer happening. All right. So good. All right. So what we've said is this is like a rough description of this is what we've seen. We've seen a bunch of examples where you try to come up with subproblems and solving them leads to the right answer. And often the analysis is by induction. The proof of correctness will be by induction. And the complexity analysis will be by writing down recurrences. Okay, so this is what we will do for divide and conquer. Okay, and conceptually these kind of algorithms are nice to think about, right? Because I mean you try to say, okay, I'll solve this subproblem and the answer will give what I want. Alright, so and I want to talk a little bit more about overlap in recursive calls, and this will also lead us to our next topic. Okay, so far we've had subproblems that don't interact too much with one another. Right? Like in the multiplication case, they did have some overlap because your subproblems were defined by these x, z, and w. Like x shows up in both of these things, but it wasn't too much of involvement. So, but you can have like recursive algorithms in which the subproblems actually overlap a fair amount. Okay, and this is what these are the kind of things we'll see next. Okay, and there are problems in which you can come up with natural recursive algorithms, okay, which like solve a problem by calling subproblems. And but it turns out that you might be doing some wasteful computation. Okay, in the sense that you might be doing the same computation multiple times. Okay, and that's kind of the motivation for what we will see next, which is what is called dynamic programming. So yeah, so dynamic programming in a nutshell is basically recursion done well. Okay, so it's I'll have to pause for a little bit. Yeah, so in some sense dynamic programming is recursion where you kind of do things, where you keep track of what you're solving as well. Okay, so we'll see that in a little bit once this thing gets charged. Yeah, you can use like a minute or so break. If you have questions about the previous thing, feel free to ask.
In the previous experiments, we wrote T of n is T of n by 10 plus O of n plus T of some constant time n.
Yeah.
So with the branching factor, we depended only on the n by 10 term because n by 10 will give more branches.
Right. So now you have to be a bit more careful about how you solve the recurrence. Okay, so yeah, so I mean, with a recurrence like this, when you draw the tree, there will be two kinds of branching. The first one will come from this 2n by 3 or whatever, and the second one will come from the n by 10. Okay? Now you can show that the 2n by 3 is what matters, because the n by 10 terms will decay way faster than the 2/3. So solving these kind of recurrences is a bit more tricky. Okay, so this is another example where this master theorem does not work, and this other theorem that I mentioned does work, but the easiest way is to guess the answer and prove by induction. Okay, so you guess that it's some constant times n, and you prove it by induction.
So for guessing an upper bound, we can use just the 2.
Yeah, you can use what's going on. You can try to expand it a little bit. See that the n by 10 term is dying out very fast. Then you guess that it's just it's just some constant times n. Yeah, you can also come up with an explicit formula. In this case, it's easy enough that you can, but but you don't have to. Yeah, very often when you're doing recurrences, you'll have to use your high school skills of like these geometric progressions and so on. Yeah. So sometimes you can just guess your way out of this. And sometimes you really need to. All right. So let's. Okay. All right. So to introduce dynamic programming, I thought I would start with a simple question. Okay. So this is again the new problem. Okay, so it's called subset sum. So as I said, the first few lectures of this class you will just see a whole bunch of new problems. So you'll have to think about each of them separately. Okay, so the subset sum problem, it's again simple. You've got a bunch of integers a0, a1 up to an minus 1, and you're also given an integer s. And your goal is to find out if there is a subset of these things that you have whose sum is s. Okay, so maybe s is equal to a0 plus a4 plus a5 or something like that. Or s may be like sum of all the things, something like that. So is the statement clear? You're given a target S, and you're given these bunch of things. You want to find the subset of these guys that add up to S. So what is a naive? How would you first approach this kind of problem?
Keep adding each element and compare it to S.
Okay, so you could try that, right? So what he's suggesting is, if your sum is less than S, try to add the current element. So maybe you have elements in a certain order, let's even assume they are sorted or something. Try to see if you can add. Will this always find the right answer? I like how you're confident that it does not find the right answer, but you suggest. But yeah, so anyway, so this, it turns out, does not give the right answer. Okay, so there could be cases where you will miss the right solution. So for instance, I think to come up with an example, maybe you have 1, 2, 4, let's say 6 and so on. Your goal is to find a 4, right? So if you want to find 4 and S is 4, then you really shouldn't be adding the first one, right? So these kind of basic algorithms have issues. All right. So what else can you do?
Brute force just take every subset.
Yeah, so the other natural thing to think of is, you want to find a subset, try all possible subsets and see if any of them sums up to S. Right? So perfectly correct solution. So try the brute force. Is try all subsets. And find how long does this take? So in particular it takes something like 2 to the n times n, maybe to add all of these things up. Right? So this is clearly exponential time. Okay, so this is sometimes this could be the best you can do, but this is clearly something that you may want to avoid. So so any other suggestions? Like suppose I want to use some kind of divide and conquer. Yeah.
So, well, we know that you can kind of find by looking at it recursively, because we know if we just, let's say we're just trying to find the first element that would go in such a set, then you would know, I don't know, if say like you have like 3 and you're looking for something that sums to 13, then you know, okay, I need to be able to also, if I want to use this 3 in there, from the remaining elements, I need to be able to add up to 10.
Okay.
So, and then once you see that, the way you could kind of do it is start and say, well, let's see if we can, if we're saying like positive integers, you could just say, if we start, see if we make 0, if we have 0, see if we can make 1, or maybe even more 0, and then see if we can make 2, and you can kind of build it out that way.
Okay, so that's what we'll come to in the end. But I want to have a simpler thing to start with. Okay, so we'll come to that just in a little bit. Okay, but another very reasonable algorithm, now that you've seen divide and conquer, it's kind of along the lines of what he suggested, is you try dividing it into halves, right? When you don't know anything and somebody tells you to use divide and conquer, you say, okay, I have an array, break it up into 2 halves. Okay, and try to solve some recursive problems on these 2. So what would you solve? I mean, clearly if there is a solution, there is some portion of the sum that comes from here, some portion of the sum that comes from here. Perhaps empty, but there is still some, but you can still divide these things. Right? So what would be a natural way of doing this? Because I told you everything is an integer. So, yeah.
Just seeing if you can get s divided by 2 on both sides, like it would be evenly divisible.
Right. So if it were evenly divisible, you could say maybe I will first look for this half with s divided by 2, look in the other half with s divided by 2, and then I would be in great shape. But you don't know if it's evenly divisible. So what you could do is try all possible divisions. And you could say there's only so many divisions, right? S is an integer. Okay, so I could say I try to make 0 here and s here, I try to make 1 here, s minus 1 here, and so on. This is another correct algorithm. It will take a long time, but this is another correct algorithm. So you've got something like S plus 1 tries. But your array size does go down, right? So the array size now goes down to n by 2. So if you think about it, you can write this recurrence, which says T of n equals S plus 1 times T of n by 2. So this is another reasonable algorithm, and the solution to this will be something like S plus 1 to the log n to the base 2. And this is not terrible, okay, so this is like n to the log s to the base 2, if you think about it. So if s is small, this is not very terrible. So you can do things like this. This makes intuitive sense, right? If s is an integer, it's not too big. You know, this, like if s is n, okay, then this is, or if s is like 10n or something, and this is like n to the log n, which is much better than 2 to the n. Okay? So this could be better than brute force. Alright, so yeah, this is something to know. Okay, but the question is, it's still kind of exponential in this weird log s term, so it's s to the power of log n. Can you do something better than this? Yeah.
So for each element, it could either be included in that sum or not included.
Yeah.
So we could have something like s over a0 to n plus s over a1 to n.
Okay, so this goes back to what he suggested earlier, right? So it's a very similar idea. So what you guys are saying is, okay, so the running time of this is okay. Alright, so now what you guys are saying is, you know, you can go element by element, right? So that's your problem, and you can try to see maybe like the true solution will either have a0 or it won't have a0. And you can try to do this kind of a branching procedure, right? Like you can say, okay, so first decide if a0 is there or not. So you try two things. One is look for s in a1 through an minus 1. Or look for a sum of s, that is, right? Look for a sum of s using a1 through an minus 1, or you look for a sum of s minus a of 0 in a1 through a1. And if either of these two succeeds, then you found something which adds up to s. Because you know, one of them, if there is a subset that adds up to s, either that subset includes a of 0 or it does not include a of 0. If it does, you will find it in this branch. If it does not, you will find it in this branch. So this is another correct solution. And how long does this take? Each element has two to the n. Yeah, so if you think about it, this is exactly the brute force solution. Okay, like you are essentially trying every possible inclusion exclusion. Okay, so this takes time exactly 2 to the n. Okay, so we are out of time. So next class we'll try to see how you can speed this up. Okay, so we'll look a little bit more carefully at this procedure. Try to see that, okay, maybe I can do something.
我是北方人，我听你说话，口音有点不对。
Sorry.
Are you going to class? Are you going for a game?